So this video is going to talk a little bit more about properties of our combination formulas. So in class we talked about these formulas. We said, hey, if n choose 0 is always 1, n choose 1 is always n. That's always the case, and in fact, you'll also get, once you have the bottom property where n choose k is always equal to n choose n minus k, you'll also pick up the fact that n choose n is always 1, and n choose n minus 1 is always n. Okay. There's a symmetry property, in other words, about the combinations. Now, the easiest way to see how that works is actually based on something that you may have seen before. It's called Pascal's triangle. And this is what Pascal's triangle is. It is 1, then the second row is 1, 1. The next row is 1, 2, 1. The next row is 1, 3, 3, 1. The next row is 1, 4, 6, 4, 1, 1, 5, 10, 10, 5. And if you haven't seen Pascal's, and it keeps going. And if you haven't seen Pascal's triangle before, stop the video right here. Take a moment. Think about how each of those numbers were achieved. Okay. Now, we look at these numbers, and specifically if we look at them by row, the first row corresponds to when n equals 0. The second row corresponds when n equals 1. Third row when n equals 2. Next row, n equals 3. Notice the n value here is just increasing by 1 each time. It also will always match the second number in your row if you have a second number. Now, each of these values in Pascal's triangle actually correspond to n choose something. So in the first row, this guy corresponds to n or 0 choose 0. In the second row, this corresponds to 1 choose 0 and then 1 choose 1. Next row, 2 choose 0, then 2 choose 1, then 2 choose 2. Next row, 3 choose 0, then 3 choose 1, then 3 choose 2, and then 3 choose 3, and you can keep on going. Let's do one more row. So 4 choose 0, 4 choose 1. Notice each time you have an n choose 1, it gives you exactly that number back. 4 choose 2, 4 choose 3, 4 choose 4, and this is actually a shortcut way of calculating an n choose k value, or having to calculate multiple n choose k values, as long as you don't go too far out, and then at that point it just gets tedious. Okay, but notice something about this particular Pascal's triangle. There's symmetry involved. So if you actually look at the triangle itself, starting with a 1 and then going straight down, notice on either side you have the same numbers going out, or if you prefer, going from the edges of the triangle towards the middle, you're getting back the same numbers. Now, Pascal's triangle is typically used to give yourself coefficients, specifically coefficients as follows. So, for example, this guy right here, these are the coefficients on a plus b squared. The next one would be the coefficients on a plus b cubed. And these are fast ways of determining how to expand polynomials, and that may have been how you've seen it if you've seen this before. Note the reason why you would do this. For example, if we pick on this guy right here, which is 3, it corresponds to 3 choose 2. If you actually expanded out this polynomial of a cubed plus 3a squared, b plus 3ab squared plus b cubed, that 3 right there would correspond to the fact that you are selecting exactly 2 of your potentially 3 b's involved. And notice here what happens if we're cubing things. Each one of those terms, if you actually add their exponents, each one of those terms are going to equal 3. That means each one of these terms has a degree 3 involved in terms of polynomial language. And so what you're doing with each of those 3 choose whatever k's, the 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3, is you're selecting how many of the factors of that degree 3 term are going to be, in this case, how I've set it up, are going to be B's. Everybody else would be the A's. Yeah, so that's one application of these n choose k things. Now notice something else about our n choose k, or our factorials, is, and let me get a different highlighter here, is for any entry in the table, any entry in this triangle, your entry is the sum of the two numbers above it in the actual triangle. Now this leads us to another property of combinations, which is simply that if you add adjacent combinations, you will get the corresponding entry in the row below. Now what does that mean? That means you're going to add two guys that are n choose k. Adjacent would be n choose k plus 1. When you add them together, you'll get an n plus 1 choose, and then an appropriate location, appropriate bottom row in your combination to grab that number that you want. Okay? I'm on purpose trying not to say what that bottom number is, so let me go ahead and actually put in the details here. So if we look at our guy down here, I'm just going to focus on 10 being the sum of 6 and 4. So this is 5, choose, 0, 1, 2, 3. So notice the bottom number here, the 3, matches the bottom number on the second guy. And this tells you that in terms of our property, we have 4, choose 2 plus 4, choose 3 is equaling 5, choose 3. So if we make that in generalities, n up top bumps up into an n plus 1, k and k plus 1 on the bottom bumps up to the larger of the two numbers, or the k plus 1. In other words, this formula right here. And this is a classic property of combinations.